This presentation devotes to introduce the importance of multi-objective optimization methods in combination of deep neural networks for enhancing and improving the overall performance of the radio frequency designs and also VLSI designs. Here we would like to focus that what is the application of deep neural networks? So we would address this question in a very professional way, I think. Automation. Automation is a very simple word, but it has a world behind it that nowadays researchers are trying to do the process in an automated way due to various benefits. For example, it is faster, it is precious to the errors, it is secured, it can be repeatable. We are working with the codes, and we humans can interface in our written codes to, for example, increase the performance or to change the specifications that we are dealing with. So nowadays, I mean that, for example, it's in the 5 years or 6 years that many researchers are working in this domain to have all of the designs in an automated process. Actually, in my PhD thesis and also in my research, I would like to have 2 or 3 or more than these softwares working together. For example, in one place, for example, one side, we would like to have the EDA tools, and in another way, we would like to have the numerical analyzers. In my power amplifier designs, I mostly use the ADS, which is the Advanced Design Systems, for designing, for example, power amplifiers. And in another way, I use the MATLAB as a numerical analyzer that I am coding there, employing the multi-objective optimization methods, and etc. So here, two various, or I mean that, for example, more than 2 various softwares are working together, and we would like to join them. As you know, for example, EDA tools is another world, and numerical analyzers are another world. So our main idea is to combine these various softwares together to enhance the performance of high-dimensional designs. Power amplifiers are really challenging designs because we have to deal concurrently with various specifications, for example, such as the efficiency, output power, linearity, with the bandwidth, and etc. Why? Because in the power amplifiers, we have an active devices, for example, such as the GaN transistor modules, which is very popular nowadays. From one side, we have the input matching networks, and from another side, we also have the output matching networks, which are combining with active devices such as a transistor, as I mentioned. So here we have various components and various type of the elements, and with combination of these parameters, we would like to enhance the overall performance, such as the gain. For example, for the gain also, we would like to have the flat as much as possible we want. So really dealing with these nonlinear specifications really is not straightforward, and we need advanced optimization methods. I don't know how much you are familiar and you're working with ADS. ADS is a software, as I mentioned before, for designing power amplifiers, antennas, and etc. And it's very popular, and it's a very successful one. And there, for example, we can use the EM simulation, I mean the electromagnetic simulation, for ensuring the first pass designs, or we can, for example, we can include the PDK models, which are the ready transistor models. In order to have the successful integrated circuits, we can use these ADS, and it has to pass the LVS, DRC simulations, Monte Carlo LVS, to see that, okay, your chip, your design is working perfectly, and it can be sent to the company to be fabricated. Without passing these simulations, it is not possible to make these layouts to the companies, because Each company require these successful simulations. And of course, it consists of accurate models and powerful simulation technologies. From another side, you know better than me, in the MATLAB, it includes a growing database. It's possible to call external libraries, and it includes free codes, and it has ability to generate the automated codes and etc. But what are the problems? While we are working with the ADS, it is not really possible, or I can say that with the EDA tools, it is not really possible to work with the iterative mathematical scripts, or we cannot really integrate various algorithms inside of it. And it really faced with problems when we have non-linear circuits, and unfortunately there is a convergence problems, even though it is the acceptable tool for the RF designers and for the VLSI designers. But from another side, when we are using numerical analyzers such as MATLAB, we can express a matrix and array mathematical directly, and it can include a large number of tools, and we can access to the large data. So from one side, we need ADS in a very simple word for the EDA tool to passing the EM simulations, for example. And from another side, we want to have an accurate results. So that's why we try to combine these various softwares together in order to enhance our performance. But how? Actually, this picture, I like my picture because it is a summary of my PhD thesis that I graduated in 2021. There, in my PhD thesis, we propose a black box multi-objective optimization methods that, as the input, we are giving the GaN transistor model as the active devices, and as the output, we are getting the ready to fabricate. It is really interesting, and it really straightforward, the tasks of engineers. There, it includes two important steps. Firstly, we have to say that, okay, what configuration my power amplifier, or as the passive devices, my antenna can include. And from another side, concurrently, we have to guess that what are the optimal design parameters for each of the elements. So we propose these black box multi-objective optimization methods that concurrently, firstly, we are predicting the suitable and the optimal configuration of each design, and afterwards we are guessing that what are the optimal design parameters of each element. So there we tested, and we of course use various optimization methods such as the bottom-up optimization, top-down optimization, and the important one is using the deep neural networks in each of these steps. And in the forward, I will describe in details. Classification and regression deep neural networks for designing power amplifiers. This publication, as you can see, in 2020, it has been published in the Transaction of Circuit and System. This is a major framework of my PhD. There, as you can see, let's start our first step. That there, firstly, we are predicting the suitable configuration of our design. You know, simplified real frequency technique, or in an abbreviated way, SRFT method, is a very popular and very famous methods for the RF designers that we usually use these methods. Why? Because it gives the initial idea how the configuration of your power amplifier can be. But what is the drawback with these methods? It's like this. It generates various configurations. So we as a designers don't know that what is the optimal and which configuration I have to use in my design. For example, imagine that it can give that for the input matching network, so you can have just one LC design, For the output matching networks, for example, you can have one LC design with these component values, or it can go to the NM structures. So I, as a designers, must predict that which of them is the correct one. So what we propose, as you can see, this is, for example, active devices. I don't know. Yeah, let me. Oh, sorry. Laser. Good. Okay. This is a transistor model, a transistor model that I had used. This is from Amplon company in the Netherlands. As you can see, while I am using the SRFT methods, it gives that, okay, you can have, for the output matching networks, you can have these various components, these various structures. These are the impedances for the gate and the drain impedances that are achieved by the measurement. And it gives that, for example, maximum power efficiency and also output power gain that you can achieve from each of these impedances. The SRFT methods start working from these aspects, that we are entering these impedances for the SRFT methods, and then it generates these various configurations. So this is just a hint. Okay, as you can see, here I have a lot of configurations. And this is just for the output matching networks. For the input matching networks, I also have 7 various configurations. So what we propose classification neural networks. What we are doing, you know better than me. We are training the classification neural networks, and it says that, okay, for the input matching, for the input layer, give the data of your transistor, such as the gain, efficiency, and output power. And as the output layer, we are predicting that which of the configuration can be suitable for us. Okay, as you can see, we have 28 configurations, and this classification deep neural networks predict that from 28 configuration, which one is the most suitable for our transistor model. For testing these classification neural networks, we are entering the optimal specifications of each transistor model as the input of these neural networks. And then, for example, you can train your classification of neural networks and give your data of the transistor. So you are just training your own deep neural network. And as you can see, for example, for the configuration with the label of the 24, we see that, okay, the probability is the highest. So this is suitable for me. Which classification, which configuration? As you can see here, for the use transistor model, for our transistor model, it says that if you have 4 branches of LC for your input matching networks and 3 branches of LC for your output matching networks, then you will certainly receive the optimal specifications that you are desiring. So I, as an engineer, become very confident that it is I am going in the correct way. Okay, we find the optimal configuration. The second step is to find the optimal design parameters of each element. Okay, now let's go. Here, we are dealing with another deep neural networks. We are training regression deep neural networks where we are, again, as the input layer, we are entering the gain, efficiency, and output power of the desired power amplifier that we obtain from the classification deep neural networks, and then as the output layer, because gain, efficiency, and etc. are the non-linear characteristics. So I would like to optimize all of these characteristics concurrently. So what is the message? Here we use the TESEMO multi-objective optimization for which is a it's a specific multi-objective optimization that is really working very well. And the basic of this optimization is the Pareto optimal front. This is a general idea of the Pareto optimal front, which means that, okay, if your values are exactly in the red line, so you are moving in the correct way. So I mean that in a summary, I would like to focus that the importance of this TESM algorithm, or I say the abbreviated way, it is a Thomson sampling efficient multi-objective optimization. Its base optimization is on the Pareto optimal front, which is finding the optimal way. Why we are using this optimization? One, because it is dealing with a multi-objective. Here we would like to work with various nonlinear functions. Second, its base algorithm is on the Pareto optimal front. As you can see, when you see this figure, so be sure that you are finding the Pareto optimal front, and these red ones are the optimal solutions. Good. To demonstrate that our proposed method is working well, as you can see, we compare with a previous one with the SRFD methods. That in the SRFD methods, for example, as you can see, the drain efficiency is not well. The red one, excuse me. The drain efficiency is low, but with our proposed optimization methods, the drain efficiency becomes high. It's not really straightforward to increasing these efficiency gain or output power together. Output power can be the same because it depends to the character of use transistor, but having the flat gain and also the drain efficiency is not really straightforward. You know, while I was in the second year of my PhD, I see that okay, deep neural networks, machine learnings are becoming popular, but the big problem was this: where we can use it. That's why in my PhD thesis and of course in my research, I would like to address this question: that what are the benefits and deep neural networks and where we are using. So as you can see, for the high dimensional RF designs, we can use this very beneficial method. Okay, as an RF designer, as you can see, we have to prepare the layout. So there we have to use the transmission lines. As you can see, these are the transmission lines of our power amplifier. And as you can see, there are many design parameters, and dealing really with these parameters are not straightforward. That's why we use the deep neural networks for finding the optimal design parameters that are also passing the electromagnetic simulation as well. Unfortunately, I had a very bad experience. Firstly, I had found a very optimal design parameters, and we were happy that okay, it's worked well, but I see that it's not passing the EM simulations. So my fault was this, that in the MATLAB code, for example, I had to written that what are the limitation of each of the transmission lines must be. For example, as a length, it must not be less than 0.1 millimeter, and etc. So if you're using these methods, please be sure that you are looking to the data sheet of these components as well. And these are the fabricated high power amplifiers. That one of them is the efficiency oriented optimized high power amplifiers, and also this is the gain oriented optimized high power amplifier. That I would, from here again, I would like to express my gratitude to the Amplum company, which fabrication and measurement has been done there. And these are the results, as you can see here. This is the S parameter results. As you can see, we obtained from the measurement and simulations, and these are the results that obtained for the output power gain and efficiency from the simulation and measurement size, as you can see, and it's appreciated because the values are the same, not the same, approximately near together. It is normal because of course in the measurement you are facing with the various errors, such as for example noise, which you are getting from the environment, and it is out of control, and these maybe some unsimilarity are normal. And these are the results for the drain efficiency and output power for each of the frequency and the linearity digital pre-distortions that you can see from the measurement aspects. And this is the results for this second power amplifier that I mentioned before. Because I don't want to face with a short of time, that's why I am not very going to in details of these results. One of the reviewers had asked that why you didn't use a shallow neural networks. That's why we compared the results with the shallow neural networks and demonstrate that, okay, while you're using deep neural networks, your performance and normalized errors are suitable for us. Okay, as you can see here, as I mentioned here, for this publication, we propose two various deep neural networks for, firstly, predicting the optimal configuration, and secondly, we would like to predict the optimal design parameters of our designs. And then, okay, we again use these power amplifiers. These deep neural networks for designing power amplifiers, which has been presented in the IMS conferences. There, as you can see, okay, we have the similar, as you can see, classification neural networks here, but we increase the characteristics of our transistor model, and we use the non-linearity and the linearity of the transistor model as well. We increase the specifications of the neural networks. Secondly, we say that, okay, of course, firstly, in the first publication, we use we optimize the gain, efficiency, output power, but linearity of the power amplifier is also this very important. So let's consider the phase distortion as well. So for this case, we train two regression deep neural networks with two various optimization methods. As you can see, for optimizing gain and efficiency, we use the particle swarm optimization. And for the phase distortion, we use the modified quicksort optimization to see that, okay, how we can optimize our high dimensional power amplifiers. Okay, this is the characteristic of our used transistor model and the CPU execution environment and the bandwidth of power our amplifiers. That's really high, and it's between 1 to 2.3 gigahertz. Okay, you know better than me these specifications that, for example, we have to, for training any deep neural networks, we have to pay attention for the number of training data and also the hyperparameters, and of course the accuracy of our trained neural network is really important. That's why in my designs I obtain this accuracy, as you can see, around 99%. So as you can see, for attaining various data, I achieved the data for the gain, output power efficiency, AM to AM, AM to PM, to have a complex 3 deep neural networks. And this is the general power amplifier designs that we obtained for this publication. Okay, and these are the designs that you can see here. I know that I don't want to face with a short of time. That's why I'm not focusing on the results and would like to focus on the methodology. So here, as you can see, we combine the ADS and MATLAB softwares together. We try to find the optimal matching networks with the suitable design parameters that not only one-tone results are obtained, but also we are working with a two-tone results as well. Okay, let's look from another aspect of deep neural networks. We are using it for predicting the future performance of our designs. Okay, here, as you can see, in my 3 various publications that I give the summary of them, we use the deep neural networks for predicting the future performance of passive devices and also the active devices. Okay, let's start with the passive devices. As you can see, this is the antenna designs that I had done in my master thesis that I graduated in 2015. We design a antenna that's the passive devices, as you know, and it's suitable for the satellite. I try to say that, okay, what we are testing, predicting data specifications of our antenna as the S11 gain, E-plane radiation patterns, H-plane radiation patterns for some bandwidths such as F1 up to Fn. But I, as a designer, would like to predict that, okay, what are the performance after Fn to Fm? So we trained the neural networks that predicting that for, in this case, what will the future performance of our antenna. With this one, we try to find the optimal hyperparameters of our trained neural network. For this case, we use various optimization methods, as you can see, for example, genetic algorithm, particle swarm optimization, and colony optimization, and etc. And there I see that while we are using the Thomson sampling, which in my transaction paper, I had also used this Thomson sampling. I said that, okay, the overall error that's occurring by using these methods is less than the others, and it's more successful in predicting the future performance of our passive devices. Okay, we predict the future performance of passive devices. Let's predict the future performance of power amplifiers, which is active devices because it uses the active transistor model. So here we design power amplifier, as you can see here. Then we change the performance of input layer performance of our neural networks here. For the input layer, we use the S parameters, gain, output power efficiency of our power amplifier. And as the output layer, we would like to predict that what are the specifications of our active devices for the bandwidth from FM to Fn to Fm. As you can see, this purple one, this purple region shows that our trained neural networks is working well and it can predict our future. Okay, in my third publication, I tried to use deep neural networks not only with the passive devices, but also with active devices. This figure is the main figure for any communication systems, for the 5G, for the 6G wireless communication systems. The main concepts are having the power amplifiers and also antennas together. But challenging with these two various designs that each of them are another world is not really straightforward. And deep neural networks make our life more easier. Why? In designing these circuits, the impedances that we get from both sides is really important. So we train neural networks for arranging these various impedances that results in optimal performance. So we train in neural networks and we change the input layer specifications with the output layer specifications in order to target to our aims. I didn't talk about the structure of these hidden layers. In all of the neural networks, I prefer to use the LSTM because LSTM layers, because I would like to have the information for the large bandwidth. That's why we use the LSTM, because we don't want to get the data for just one point. we would like to have the data for the large bandwidth. That's why we try to have the LSTM layers. This is the complex structure of these neural networks, as you can see. Okay, here we are for the passive devices, we are using the CST and also MATLAB. And for the power amplifier, which is the active devices, we are using the ADS and MATLAB together. So these are another worlds, really. From one side, we are designing passive devices, as you can see, as a phase one. For the second phase, we are designing the power amplifiers, which is the active devices. Then by using these neural networks, we would like to find the optimal impedances, which results in a high performance results and outcomes. Shortly, I would like to say that this design is the MIMO designs. It's the MIMO antenna designs, and this one is the MMIC, which is the IC designs, real IC designs, because of the use of a real transistor model, as you can see. Okay. We are using neural networks for predicting the nonlinear performance of the FinFET transistors. Previously, we used it for the GAN transistor model, and here we would like to demonstrate the performance for the FinFET transistor models, which we did it with dear Professor Simona Donati from Politecnico di Torino. Okay. FinFET nowadays becomes very fashion because it has a very good performance in various domains. This is the general structure of the FinFET transistor model, that it includes the bulk, insulator, source. Okay, I don't want to go inside of these aspects, but I would like to say that how I can model this FinFET transistor. For modeling these transistors, we can use the polyharmonic distortions, X parameters, or for example, we can use the Pada models. You know, generally for the designs, we have two parameters, S parameters and also the X parameters. X parameters are the more exaggerated form of the S parameters because we are including all of the harmonics there. That's why we prefer to use the X parameters in our designs, but it's not, of course, a straightforward. This is the general structure for, the crossbar of our transistor model, which includes that, for example, what is the width of the drain, what is the width of the source, and etc. Okay, good. But here I would like to model the large signal of my transistor model. In this case, we are using the TCAD model. It's a very beneficial tool for extracting the X parameters of our transistor model. And then we are training the deep neural networks and etc. That in the following slides I will show it. So in a summary, as you can see, we would like to define this FinFET transistor model in one model. As you can see, as the output, while we are using the X parameters, we are dealing with a large number of data, as you can see. For example, this is the input signal, but while we are using the X parameters, as you can see, I have a lot of data, and it's random, it's not really in a very concrete way. So we have to deal with these complex numbers as well. For this case, there in the X parameters, there are two different specifications, such as the A parameters and also the B parameters, that there as the input layer, we try to explore the real and imaginary of the A parameters, and then for the output layer, we would like to predict the real B11 and real B11 and etc. As you can see, 1,1 shows the harmonics of our transistor models. This is the general definition of the A models and B models. As you can see, it is a bit complex definition. As you can see, these are, for example, X, F, X, S, and etc. are generated from the TCAD tool that I had explained before. So here, as you can see, These are the experimental models that we achieve from the equation 1, and these are the data that we obtain from the DNN model. And as you can see, they are approximately near together. Sometimes this for RF designers and VLSI designers, this is the main question, that why you are using more than 2 hidden layers, and this is the answer for these questions, that while we are using more than layers, our accuracy can be increased. And this is the loss of our trained neural networks. Okay, lastly, we can also use deep neural networks for CMOS designs. It's a great honor for me to be as a co-author with dear Professor Hassan Najafi, and also dear Dr. Sercan Aygün, and other professors from Istanbul Technical. And fortunately, about after a week, we will present this presentation in Germany. Here, we use MATLAB, Cadence, Python together to enhance the performance of our VLSI designs. What is a VLSI design? It means that it is the integrated circuit which is designed using the CMOS transistors, which is different. So as you can see, this is the main structure of our proposed methods. As you can see, it's very complex. We are dealing with various tools together. So here, I am describing the part that I did. Let me firstly show, okay, this configuration, then it will be okay. Okay, as you can see, this is the CMOS designs for the logic gates. For example, this is for the inverter. As you can see, this is for the XOR gates, logic gates. This is for the...
On the previous slide, the SC, is that stochastic computing? Can you go to the previous slide? One more back?
Yes, exactly. Exactly true. Okay. Okay, this is the CMOS designs. It is different from the previous transistor models that I described. We use for the RF designs, okay, we can use the gallium nitride transistor models, FinFET transistor model, but while we are using with the VLSI designs, it is appreciated to use the CMOS designs. Okay, here this is the XOR transistor XOR configuration. And this is for the multiplexer, this is for the NOR logic gate, and it's for the NAND logic gates. Okay, this is my idea. You know better than me. For the stochastic computing, delay is really more important. So we would like to challenge with this aim, how we can decrease the delays in the stochastic computing. We say that, okay, instead of using the ready to fabricate or ready package that exists in the Cadence software, which is a really powerful tool for designing VLSI circuits, instead of it, okay, let's propose our own logic gates. This is our own proposed logic gates, but we would like to say that, okay, what are the sizes of these CMOS transistors? What are the widths and what are the lengths of each? For this case, let me go to the previous one. For this case, we trained the neural networks where for the input layer, we have the widths and the lengths of the CMOS transistor. And as the output layer, we are dealing with two specifications, such as the latency and the power consumptions of each designs. And again, we use a Pareto optimal front, as since in the power amplifiers designs, we see that, okay, it works very well. That's why we use exactly these optimization methods that I really enjoy this optimization, because it really works very well. So by using these trained neural networks, we obtain these optimal parameters of each transistor model. And then here we are demonstrating that where we can use these, I mean, the concept of the stochastic computing that my friend Dr. Sercan has done it. So here I would like to express the part that I did. Of course, in the cadence, we design our own logic gates, and then we say that okay, for the image processing and etc., you can use it, and it is performing in a very suitable way. So here we use the LSTM based deep neural networks for not only optimizing latency, but also power consumptions together using the Pareto optimal front. And you know, Cadence has various versions. We use the 180 nanometer, and it's really good, and we didn't see any problems with them. So here we try to, as just a minute to show it here, we try to combine MATLAB and Cadence together. That Cadence itself has a license that you have to request the Cadence to send you the license of this Cadence to make a collaboration between MATLAB, and really we deal a lot to achieve it, but thanks to Cadence for providing it to us. So it's straightforward your performance, and it lets you to apply the optimization methods that you are dealing. I think that I am on time, because I would like to give a fortune for 15 minutes for any questions. Thank you very much for your listening.